Good morning, good afternoon, good evening, everybody from east to west. This is Dr. Ali Bakr speaking about our topic today, the application of the artificial intelligence and machine learning on seismic interpretation principally. Before I start, I just give you some information about myself. My name is Dr. Ali Bakr, and I was working on this field almost 42 years, since actually 1980. I graduated from Alexandria University in Cairo, and I got my master degree and my PhD from Cairo Leicester University. Actually, my examiner are principally from London, from Leicester, and I'm principally a geologist by graduation, and by experience, I'm explorationist and geophysicist. So I worked on all kind of companies, about 6 or 8 companies. Some of them are majors like Shell, Phillips, Apache, and some of them are small companies. So I got most experience on data acquisition, processing, interpretation, and then now actually I have my private entity, Rockserve. We're doing a lot of services for the upstream structures of the business, starting from seismic and ending by even dynamic and static models. At the same time, we're presenting a lot of courses for upstreams. Okay, this is all about me. Now let us kick off and start talking about the subjects that we are going to talk about today. I started with these first slides just to give you an to let you be familiar with what we do on the exploration. So this triangle is interesting triangle where a lot of stuff are engaged on it. So from the left hand side, you have the interpretation of the seismic, and then you go up to the triangle with the seismic interpretation, seismic stratigraphy, amplitude, spectral decom, trace shape classification, and this all end with what? End with volumetric. From the other side, quantitative interpretation are integrated with AVO, with rock property, with scenario for 3D float prediction, or even 1D float prediction. And in the middle, actually, you are integrated all the gravity, magnetic. So all of this data are integrated into one crucible to give you what we call it volumetric value for the property that we are dealing with. Taking this in consideration, we will focus only on just some part of this triangle. Of course, we don't have the time to focus on this, so we're going to focus into the seismic itself. Either it is a structure interpretation, a stratigraphic interpretation, all from the other side of the triangle on the quantitative interpretation. Those are the three types of interpretation that in the geophysical part of the exploration we are doing in hand. I'll start with the simple graph with the interpretation, which all of us are principal talking, and you know exactly what it is, which is the fault mapping parameters. So all the job for the geophysicist is mapping the faults, and mapping the faults needs what we call it fault mapping parameters, which include a very simple stuff like the fault plane, the fault heave, the fault polygon, the fault stick, the fault strike, the fault thrown, and there is another actually rather than those six parameter, including the fault depth, the fault azimuth, or you can add a lot to this, but actually those are the principal parameters that you need them in order to map fault. I think that 70% of the time of the interpreter, especially the geophysicist, they spent it on mapping the faults itself. It's very hard job, especially if you are working in a very complicated area. Then you are talking about at least 500, 600 faults. You have to map them using those mapping parameters. I'll give you just a small example about how it is done. And this is a cross section where you have, and actually I borrowed this from a presentation for SLB, and you have this seismic section, and you have a time slice from the variance or from the semblance. And what you see it here is as a line is representing the strike of the faults. As you can see, there's many hundred of those faults. If you are spending at least 10 minutes per fault all over the volume that you're working with, this means that you're going to spend months and months working on such kind of data in order to tie in the real 3D model of interpretation, to tie the fault strikes those lines are representing, and the fault sticks, as you can see it as the blue line here representing the stick. So tying the stick with a strike in order by the end of the day determine where is the fault plane is. I'm going to show you this directly now in an alive shape. Let me know if you don't see the movie itself. If you cannot see the movie, it may be related to the internet, but I think it's a simple one. You can see it directly, and this is actually how we connect the fault plane from the fault stick to the fault strike at a fault mapping parameter. This normal procedure take, as I mentioned, months of interpretation, and applying the artificial intelligence will play a very good role in order to, first of all, map all of this fault plane rather than from the sticks or rather than from the strikes, but directly using the artificial intelligence itself. What does it mean? It means that a lot of data can be done in a short time, and this is the beauty of the artificial intelligence. As you can see, a lot of faults need to be mapped. That it's not mapped here, as you see, either minor faults or big fault. By the end of the day, we should see all of them. So for the interpretation, actually, we are talking about structure interpretation, as you see on the fault, and we are talking about stratigraphic interpretation, including seismic stratigraphy and using seismic stratigraphic attributes plus seismic inversion. And then the third type is the quantitative interpretation, which is deal with the fluid itself through the AVO and AVO attribute. So those are the three type of interpretation on the seismic, and actually applying the machine learning and artificial intelligence in each one of them is included, and each one of these steps does have some of the application of the artificial intelligence. Actually, my procedure during the lecture is to, first of all, to give you a flavor about the theory, and then a flavor about how we apply this, and then by the end of the lecture, we are going to have 10 examples. Those 10 examples are covering the different type of interpretation, at the same time showing to you how the AI and the ML are serving us on doing a better job in a short time. This is exactly what I talked about. You have the first one, automated seismic interpretation, structure interpretation workflow, and then automated seismic stratigraphic interpretation workflow, and then the last one, quantitative seismic interpretation workflow, include AVO and rock properties. Those are the three, principally are the three type of interpretation that's done in the market. But actually, the artificial intelligence or machine learning are not starting from the beginning to the end in any one of them, in the structure or on the stratigraphic or even on the AVO and rock attribute. It's are included within the workflow itself. So as example, in the automated interpretation of structure interpretation, you have the 3D seismic, you tie the seismic to geology, and then you do attribute as a variance, depth, and other attributes that cover many attributes for the structure attribute. And from that attribute, you collect what we call it multiple attribute together, and then using this attribute in order to manually interpret the faults, as you see on the first slide and the second slide. And then you build your fault surfaces, and from that you started to have some sort of structural model. When you put just your horizon, so you put your stakes, you put your strikes of the fault mapping parameter, and then you fill in the horizon, and then you have an end interpretation of structure interpretation. This is a normal way. What we do actually, rather than doing the faults in a manual way of interpretation, we are using machine learning and artificial intelligence to do the fault itself. So we save the main maximum time that was spent on all of this. Actually, if you divide your time on these steps, you will see that these steps only take almost 70 or 75% of the time mapping the faults itself, and then maybe the other will take the other 30%. So actually, we engage the artificial intelligence in just a step, just to save the time and have more accuracy for the fault mapping itself. Now we jump to the automated interpretation of the stratigraphy. Actually, the stratigraphy, what we mean by it is to map as much as we can of horizon and come up with termination on lap, top lap, base lap, whatever the feature that we are looking for. At the same time, mapping almost all the peaks and trough within the volume that we are interested in, and also at the same time using the different attribute like spectral decomposition and the other stratigraphic attribute in order to extract the geobody itself. All of this seismic interpretation, this is what we call a stratigraphic interpretation. Where is the II and LE are helping us? Are helping us for mapping any geobody within the subsurface and extract this geobody either in the time domain or the depth domain and extract it outside itself. Not only this, but this can be done using unsupervised machine learning. But if you make the application to supervised machine learning from some wells, then actually you can come up with many interesting things within the geobody itself. As example, you can come up with the percentage of sand, percentage of shale, sometimes the porosity. All of this can be done using the artificial intelligence and machine learning. On the other side, that the large number of horizon can be picked. There are some softwares in the market. This software can help. I think it's called Bariscam. Can help you to map all of this number of horizon and come up with those termination very clearly. But now the machine learning actually is taking over, and it can do the same job like like this job. So in case of the stratigraphic interpretation, also we have some applications on there. Jumping to the third one, which is the quantitative interpretation, also the machine learning started to jump in, and I think I expected on the near future that the machine learning maybe will take over the inversion of the step of the inversion that's needed for detection of the fluid through the pre-stack data through the AVO and rock properties. Okay. The automated seismic interpretation is with application. Why you need it? Why now? And then actually this is represents some sort of agenda for what we need to talk about. So what are the machine learning? We need to have some definition about the machine learning and artificial intelligence within our domain, which is seismic. Why now? Then we would go to some terminology and definition. Then we will talk about types of the machine learning itself, and then we'll give you some examples for the application. Those are the 10 examples that I wanted to share them with you, and then we will maybe refer to the machine learning and computer power that you need in order to run such kind of work. Okay. Just I know that maybe most of the attendees today know about the different type of the artificial intelligence. The ANI, AGI, and ASI, where it is the artificial intelligence narrow one, very narrow one, as when you look into Google, and then you look to whatever the subject that you would like to search for, and then the Google will, for the second time, will come with a list for you. This is a kind of the artificial intelligence, a small one. Then the next one, artificial general intelligence, which is a little bit like Tesla, like playing chess with the computer. This is a second one. While when you go to ASR, artificial super intelligence, this is exactly what we are dealing with in here. Another stuff you need to make sure about it, the difference of the word of the artificial intelligence, machine learning, and deep learning. All of them are artificial intelligence, because actually this is sometimes very confusing when you read them on the books or even on some of the presentation. All of the 3 steps are artificial intelligence. So the big body from outside is called artificial intelligence. Once you have subset of this symbol AI, and then including some statistical technique, you are going from artificial intelligence to machine learning. While if you put some algorithms more into the artificial intelligence, you are talking about deep learning, and I guess that most of our work is within the deep learning itself. Okay, the deep learning and artificial intelligence could be supervised or unsupervised or semi-supervised or reinforcement learning, but actually we are not going to each category of those category and talking about it, but we are going to restrict our work into the supervised. The supervised machine learning, it looks like the teacher and the student sitting, and then the teacher is supervising the student and learning him how to do things. So this is what we call it supervised. So you teach the machine how to do things. Unsupervised, no. So the student is sitting by himself and getting him more information from the books, and this is exactly what we call it unsupervised machine learning. So we let the machine to test the data and describe the data internally, and also at the same time arrange the data into categories. Each category have some descriptions that is different than the other clusters. Yeah. And then sometimes they'll have semi-supervised, so we combine both of them together and we come with what we call it semi-supervised. And then the next one is reinforcement. We push the computer to do a solution that we needed to go through. Actually, most of the work within the seismic is unsupervised and supervised machine learning stuff. Yeah. Give you some sort of idea about the neuron and what we call it. The neuron is the cell inside our memory or our head, and this memory, at example, the child when he born for the first time and he see a cat on his coconut, he will see the cat, and then the picture of the cat will be printed inside him. His coconut and by neuron, and different neurons will look at the same picture of the cat, and then from that he learned that this is a cat by defining the characteristic of the cat itself. This exactly happened within what we call it the artificial neuron, not the natural neuron. And actually, as I mentioned here, most of the neuron will collect the weight of the picture, of the weight of the shape that they see, and then they will keep an output determining that this is a cat. So the first neuron will see it, he will recognize a cat, and he will send a signal. The second neuron will look at it, he recognize the same cat, he will give it to the output. If number of neurons accepted that this is a characterization of the cat, then he will give the signal to your brain that this is a cat. Actually, the artificial intelligence doing the same. So each neuron that we put it within the medium that we would like to test it directly without any supervision will look different neuron for look different areas or different cluster. Each cluster will have some characterization that different than the other cluster. So one neuron will be attended to this cluster, and another neuron will attend to a second cluster. By the end of the day, you have different clusters, and each cluster got different stuff, different. In our mind, like cat or dog or monkey or whatever will represent a cluster. So the neuron itself will look for all the other, and all of them, each neuron will have a different characterization for the cluster itself. The same idea we apply here, and actually why we would like to have the machine learning artificial intelligence for 5 reasons. First of all, we can analyze large amount of data simultaneously. This is a very important part. Let me give you an example. If you have velocity and density, velocity of the rock and density of the rock, they have a relation to each other. When the velocity increases, the density decreases, right? It's vice versa. You can very easily cross-plot the velocity versus density and look at how they behave. Very simply. Then if we added to the velocity and density the water saturation, as example, you can look at the 3-dimension and see how they are variable. Velocity, density versus water saturation. Now, if I added a 4th variable or 5th variable, then your mind cannot look at a 4 variable at the same time. Our mind is set to look for 3 variables only, not more than this. But actually, the computer got the ability to look for 20 variable at the same time. The problem is that he can look at them, but he cannot represent it for me. I have to find a way to represent how this variation, but this variable again should be either with 2 or 3 dimensions only. And this is exactly what we call a dimensionality problem. So the dimensionality problem is our problem, not the computer problem, that our mind and our visualization tool, which is our eye and our brain, is not designed by Allah that it can see more than 3 dimensions. We will see how we will deal with this if I have 4 or 5 or 6 or 10 variables, how I can learn and teach the computer to show me the difference in the variables themselves together. Number 2, determine relations between different type of data. This is exactly what I said, that more than 3 types. Number 3, discover the non-linearities in solution. Usually, if the variation is linear variation, you can detect it. But if it is non-linear, then it's going to be a problem. Again, this is also the computer can help me on this. Number 4, improve efficiency and accuracy over time. Of course, if you have the ability to look for different scenarios and then and different output, and you can minimize the uncertainties, then you are improving the efficiency. Number 5, the automations, instantaneous adaptation without human intervention. Exactly. And this is the last one, that by the end of the day, you don't like to put your hand and you put your mistakes, but you let the computer to review for you all what we did and discover the mistakes by yourself. This is why I'm gonna give you the example that I just mentioned minutes ago. If you have a cross plot, as example here, with acoustic impedance and Poisson ratio, and all of us know that this is, you can separate the different segment for the oil sand or water sand or shale just by plotting the Poisson ratio against the acoustic impedance. And this is one of the very interesting 2D cross plots that we do when we study the rock properties itself. If we jump to a 3D cross plot, you can put 3 variables and you still can rotate those 3 variables in the 3D vision and come up with some understanding of the behavior of each single variable. Now, how we solve the problem of the dimensionality of different variables at the same time, and why we need that? I'll give you an example. Say I would like to do a structural interpretation, and I have, as I mentioned, I have the dip, I have the throne, I have the strike, I have the stick, I have the heaves, I have the fault polygon, I have all the mapping parameters. Each attribute can bring me one of those mapping parameters. As example, if I put the variance as one of the attributes from any software, from the variance or the coherency, I can predict where is my fault strikes, all the fault strike, or the semblance can give me the fault strike, or the chaos can give me the fault strikes. All what I mentioned are a structural attribute. Now, how can I make relation between the same attributes that give me the same parameter? So I would like to get the strike of the fault from the variance, from the semblance, from the dip, from the azimuth, from each one of them. So I can let the computer work with these variables, 5 or 6 or 7 variables, come from 5 or 6 attributes, and let the computer come up with relation between them. And the computer can tell me that not all of these 5 or 6 attributes are useful in my case. So he will select for me the best attribute for me. So 2 things we need to learn: the SOM, or the self-organized map, and another variable will come to see how this works. The guy who started to show us the SOM map, which a map that will solve a problem of dimensionality of the different variables. This is him, Tuvo Conan. This guy lived from 1960 to 2000, and he came up with an interesting stuff. He tried to study the all world countries by studying the standard of living of each country, and he divided the whole countries that he studied, about 117 countries, 117 countries. He studied them and he come up with some sort of relation between countries that have the same standard of living, the same language, the same way of living. Uh, Directly as example, he put the United States and Canada in one category because they have the same standard of living, the same style, the same everything. And he did this by a very interesting way. In the front view, he divided the countries into 13 horizontally and 9 vertically. And those are, if you multiply 13 times 9, those are the 117 countries that he did. And he represented the countries by hexagon. Each hexagon represents one of the neuron. So each neuron is representing either one country or two countries, but they have almost the same or semi-identical, the same character that he used for this division. So as example, if I go to, as I mentioned, to Canada and USA, this hexagon, the one that looks like orange, no, actually it looks like yellow, the yellow one is representing Canada. So your eye will directly, rather than looking for 10 attributes used to differentiate the different countries, you are looking just for color to tell you that Canada and USA having the same attribute. Yeah? Okay, if I mention as example Egypt and Morocco have the same bench. So Egypt and Morocco very near to each other. So as an attribute, if there are 10 attributes, you can differentiate between different countries accordingly. So directly, if you look at this color, you know that this is Egypt. If you look at this color, you look at USA and Canada. Can you separate between USA and Canada? The answer is yes. If you just make this color into two different colors, you can directly look at them. So the division into 13 to 90 doesn't mean anything. It doesn't mean some sort of resolution. If you added more, as example, you made this 19 or you made this 20 and you made this 10, then you're going to come up with other hexagons, large number of hexagons. But in this case, you are not going to see the relation, the near relation between country and the other. Yes? Actually, we took the same basic method that this guy used, and we applied it on our work. But actually, why we see it? It reduces dimensionality of the analysis, determine the amount of classes that control details on the analyzed volume, and then it can be used inside without well loggings, but classification result may be used to incorporate with the well logs. And actually, this is suited for the large big data. When you have large big data, the SOM can help you on this. Now, the other important parameter that we need to talk about in order to classify our data into using the SOM is what we call it principal component analysis. And this is actually a part of the statistic and geostatistic branch that we use. As example, you have variable A, you have variable B, and then this dot represented the different dots. So linearly, this dot has one axis, very long axis, and another perpendicular shorter axis. And in this axis, you have different, what we call it, the eigenvector, where this is the main line, or they call it the first principal component, FBC, or first component analysis. And this will tell you that in this direction, you have the maximum variation. And actually, it looks like when you have a camera, you can look from this direction by your camera and look how many dots here difference you can see. And then in the second direction, you can see how many dots on the can see without losing most of the information that come from this method. So we have the first principal component and then the second principal component. Of course, there is a third principal component if we're talking about three-dimension type. We need the SOM and we need the principal component analysis in order to solve the problem of the dimensionality of the data, and that led us to conclude what the computer or what the AI and machine learning found by analyzing 20 variable or 10 variable. It will give me the result, and I'll take the result and I use the sum and I use the BCA in order to display this data in the front of me in a 2 dimension, so I can look at this variation in 2 dimension rather than the 10 dimension. without losing any kind of data. This exactly explains what we are using. How we do that? Very simple. Now we learn the principle, we learn the problem, we learn the way to solve the problem, and why we do it. We do it in order to save time and they come up with a conclusion about our data. So, as example, you have a survey, and this survey is 3D seismic, and then on this 3D seismic, you calculate 10 attribute as example, structural attribute. So your target by calculating attribute is looking for fault, as example. And looking for faults, you need to learn the parameter, the fault mapping parameters, which include the fault strike, the fault stick, yes, the fault polygon, the fault thrown. All of these are parameters. So you need to get attribute that look for this parameter, and then look at them all. Say I have 6 attributes. Then I will teach the computer about those parameters, and then he will go ahead and he will look at the similarity, at example, between variance and coherence. And if he finds that the variance and coherence are accepted one direction for one fault, then he will build up this direction, and he will look for other attribute in order to confirm the direction of the fault, and they come up with one hexagon that represent one neuron that represent that those attributes are confined to that fault only. Then another one, he will look for another fault, third one for look at third fault, and so on. Each one from this hexagon that represent neuron is colored by a special color. So I can directly, when I look at the color, so if the color, as example, is black color or yellow color, I can look directly for the fault that have this kind of color. Or even within any geobody, you can do the same. So this is the idea. And actually, the sum is not related anymore into the resolution of the seismic. The resolution of the seismic, the normal resolution of the seismic, is quarter lambda, as example, and it is variable from the shallowest part of the seismic section to the deepest part. So we are losing the resolution as you go deeper because the frequency is lower. So as example is if we are looking for a reflector at shallow part, say 1 second, then I can say that that 100 meter is lambda, so quarter lambda is 25. Then my resolution is 25 meter. This means that if I have a bed that is less thickness, its thickness less than 25 meter, I may be well not able to see its top and bottom. This is my normal resolution on the size. While actually in our case, we are not talking into the vertical resolution anymore. We're talking into about vertical sampling. So if your sample is 1 millisecond, your sample 2 millisecond, your sample 4 millisecond, you are restricted into these interval thicknesses. So if my sample is 1 millisecond, this means that I can see a resolution into the sum that is more resolution than the normal seismic. Which is the beauty of this work, that if you have a target that is very thin layer, and this thin layer is pregnant with oil or gas, then I can teach my computer and tell him that this is only 2 millisecond or 4 millisecond or 4 millisecond or 5 millisecond. Please go ahead and follow it and show me the hexagons that represent this bed all over the area. Look at this. So I'm not restricted to the tuning thickness as you can see here, but I am restricted into the sample itself. And I'll show you by the end of this how this example is there. The second step is the stratigraphic interpretation. So this is concerning the structure interpretation that the computer using the artificial intelligence can help me directly to pick up my faults in a very high optimistic and high detection methods. At the same time, it can tell me how it's complicated together, how they are terminated together. And I'm going to show you some of the examples that actually SLB, Schlumberger have did a very good job on this. Now, finishing the structural interpretation and come up to the stratigraphic interpretation. The concern of stratigraphic intervention is two things: how much reflector you can back from bottom to top in order to come up with the stratigraphic model of the area. As example, in the front view, as you can see, sorry, as you can see, you can, let me bring laser pointer. As you can see on the laser pointer in here, there is here some parallel concordant reflector, and here is some of the prograding sequences. And I'd like to map all of this prograding sequence in case of, in our case, without using the artificial intelligence. Some of the software, one of the software that show this example, is you can go through the volume itself and teach the computer how to go through all of this, give him some seeds, and then the computer can take off on this. But this is the start. There is another thing that you can directly give the computer the full volume without any seeds, and the computer will go and he will go for each peak and will come up with the pattern of the either concordant pattern or prograding pattern. And other things actually is any geobody within your area, the computer can go and depict this geobody. And I'm going to show you one of the examples that we published this example last year on the SEG convention, an SEG meeting here in on Alamein in Egypt. One of the very interesting stratigraphic mapping of deep marine channel that goes almost for 30 kilometers inside the sea, but actually we choose the part of it. I'm going to show this example by any means. So the stratigraphic also can be done using the machine learning. Now, the quantitative interpretation, and what we mean by quantitative interpretation is looking for the far and near volumes from the seismic in order to make a prediction of the petrophysical parameter. Again, also the artificial intelligence can work sufficiently on such kind of work for looking for the similar hotspots or the similar sweet spots that we are looking for. And in this case, we are not using the unsupervised machine learning, but we are using the supervised. So if you have, as an example, if you have a well or two wells, and those two wells got some very interesting characters within the lithology, within the water saturation, within the hydrocarbon content, and we can directly from that well teach the machine about those character on the seismic, and then he will go and follow any other spots that got the same parameters on there, and it will end that you map them on the 3 dimension. This is concerning the quantitative interpretation, and actually the quantitative interpretation including also the inversion, the structural inversion. And I believe that either it is deterministic or stochastic inversion, as you can see in here. All of this can be used within the inversion, within the artificial intelligence. We can teach the computer how it looks like our model after the inversion. And from that, you can go and look into our data and define for me the sweet spots that have the same parameters of porosity, the same parameter of fluid content, or any others. It's very interesting, actually, and it's going to go of some sort of revolution is coming very soon on this trend, either on the structure interpretation influencing the artificial intelligence, stratigraphic interpretation influencing the AI, and then the QI influencing the artificial intelligence. The three will have a lot of jumps on the geoscience by applying this kind of new techniques. I want to do the most important, this is the most important slide on all my lecture today, about the 10 applications that have been published all over the world from different disciplines applying the AI and machine learning on the seismic interpretation, either it's structured, stratigraphic, or even QI. First of one is the fault detection. So you can do a fault detection using machine learning, and there is a lot of software in the market doing that. Of course, SLB is a pioneer, and Geophysical Insight also is a pioneer on such a kind. Both of them are introducing a very interesting stuff for fault detection using the machine learning and artificial intelligence. Then unsupervised multi-attribute machine learning for 3D stratigraphic facies classification in carbonate field. And actually, this is a very interesting one. When you make a facies classification without going to such kind of deterministic or stochastic, but the facies classification will depend on the work of the machine learning that will help us on this. Then again, geological pattern recognition from seismic attribution, by applying principal component analysis and self-organizing map. We'll show you all of this stuff on the next slide. I'm just going through, flying through them. Then interpretation of DHI characterization with machine learning. We do direct hydrocarbon indication using the machine learning. And then multi-scale fracture prediction in area of the fracture reservoirs, how we can predict the fracture direction and magnitude and everything using the machine learning. Then even we can net reservoir discrimination. We can discriminate different reservoirs using machine learning. Facies classification using machine learning. Seismic interpretation below tuning thickness, as I mentioned at the beginning, that we are not restricted to the quarter lambda, but we are talking about the sample interval or the sample rate that we are doing. Then we can even look for subtle fault detections. This is very important on the some of the fields. If you don't have any clue to map those subtle faults from the normal seismic, you can get into the artificial intelligence and look for subtle fault. And sometimes subtle faults are very important to separate between different compartments that have different pressure regime. You can look at them, sometimes very important for simulation for the reservoir engineering studies. Application of machine learning for detailed reservoir description. As you can see, 10 steps having different varieties of trends for the application of the AI and the machine learning all over the world. All of those 10 have some publication into the SEG, AABG, and SPE shows that those have been applied. Now I'm going to show you some of the examples, and I think this example is done by Geophysical Insight. And actually, as you can see, first of all, the computer will go to the run, and this only one inline. I think it's an inline, yes. And the software used the CNN for probability computed, and they come up with, as you can see, with the strikes. With the sticks of the fault, and actually those sticks are connected together, and then it will come at the time slice, and it will give you the strike of the fault. And actually, it goes through different steps. It not directly will bring you to this nice shape of the section, but it will start with that shape, and then doing some analyze and filtering out some of the noise. And then it will come up with almost the most probable shape of the fault sticks itself. Then actually, this is from SLB, as I mentioned here. You can, in 3 dimension, put those fault directly into fault plane together. And even you can get different trend of those fault. As you can see, there is some trend going to north-west, southeast, some trend going almost east-west. Another trending are trends northwest, southeast. So it can capture all the direction of each fault. At the same time, you can tie this tectonically into the fault direction, and also not only tectonically to each time, to geological time itself. As example, this is actually from SLB again. So each fault from those faults, you can map it directly in here. And at the same time, you can categorize them into direction. So as example, in this example, we categorize only the northwest direction into this diagram, and we color it by blue color, and then we can get it directly, so you can see the strike of this blue colored fault, and also the sticks of this blue color fault. So you can relate, as example, this tectonic is belong to a certain time of the geological time. You can switch to the another direction with another color. It's set to a second color, and look at them. It will help you a lot on describing this fault in a short time. Think about if you try to map this such kind of complex shape of fault pattern that got at least three trends in three directions, and there are a lot of intersection between these trends, and you cannot judge which is which. While here, actually, you can classify them into different direction and relay each direction into a special tectonic, and they come up with some sort of analyzing all different types. I'm going to show you an interesting example. Again, this is from SLB. To the left is the auto tracker, the normal auto tracker that all the geophysicists is using. And you can see that a lot of the faults are, the auto tracker did a very good job on putting the faults and on mapping the horizon itself. Yes? But actually, it is breaks down on mapping the area in between. It didn't do any good job on there. And actually, to the right is a AI or machine learning using the for the tracking the horizon, and you can see that all of this area, almost all of this area, have been covered in a very good manner using the AI and machine learning. Interesting, and because actually, as I mentioned, this is very, very optimistic. Not only optimistic, but actually it's very close to picking the peak or trough, but not only the peak or trough, but the sample, the maximum peak or the sample of maximum peak or maximum trough for the picking itself. That's why it come up with better picking. Again, you can see how the quality related to the seismic of the picking itself and of the fault strikes itself, and even on the directions of the different fault themselves. Very, very good. Of course, anyone can say, oh, it's data dependent. Of course, it's data dependent. If your data is not good, it's not going to give you the best picture. This is another example, very interesting example. Actually, we run it ourselves using the Geophysical Insight software. Here, this is in Egypt. And actually, to the top, you have on the Western Desert in a very common field. And actually, this is a part of the PhD of one of our students. And actually, this is what we call it common horizon. It's an upper Cretaceous horizon. And you can see the faults. Some of the faults are trending northeast, southwest, and the other faults are trending northwest, southeast. And actually, you can conclude this direction of fault, and this is the common horizon, even from the variance directly. You can see that these faults echo are there. The northeast, this is the older one, and then the younger one is trending northwest, southeast. Yeah, and there is a very nice anticlines are coming there. Giving the data of the attributes and using the sum maps as we use and using the principal component analysis, we come up with almost another figure. The two slides, those two slides actually are coming from the AI. Those two slides are used for the normal conventional way of mapping. As you can see, it's one fault in case of mapping manually, but actually in case of mapping using the artificial intelligence, it's kind of different different faults, and all of those faults are forming some kind of in echelon shape. And actually, there is a kind of Stratigraphic force in here that is showing this in echelon shape. And actually, the very interesting, the different blocks here are very clear due to this kind of in echelon fault, while they are not here shown on the map that's mapped with the conventional method as one segment. A third thing is actually those different segment of fault got different thrown at the fault itself, and it's very clear in case of the AI, while in case of the convention is not showing it. So look at the details that we can get it from the AI rather than those details are not shown in case of the conventional method. Yes. Actually, what in case of the stratigraphy, actually we are going to show you another. So I just put in the front of you the structure at the previous slide, and now we are going to see some sort of stratigraphy about this. So we go to the survey, and then we calculate attributes, and actually from this attribute we are focusing which attribute are concluding into our neurons, and say I have 4 neurons, 1, 2, 3, 4, or 10 neurons, or 40 neurons, whatever the number of neurons, or even 117 neurons at the start one. And from each neurons will collect the information about one cluster. So if I have 100 cluster, I'm going to have 100 neuron. Each neuron is restricted to one cluster. Then I'm going to give each cluster or each neuron a color, and this color will describe this cluster on the displaying itself. This is very easily. We did the same actually in case of an interesting channel. This channel is an offshore channel, and this belongs to Shell. And again, this is another part of study done during a PhD for one of our colleague working on Rashpetco. This is a joint venture company between Shell and EGAS authority in Egypt. And actually, we use this data just to apply the same concept. So we have one channel that extends almost to more than 30 kilometers from the land to the sea. And actually, we just restricted our work into the southern part of the channel in here. And we just asked the computer without any calculation to do unsupervised machine learning. And then actually we used this some maps in order to look for just those restricted number of neurons that include the yellow, the green, the orange, and then the red neurons. And then we displayed those neurons into our volume, and it come up with a very interesting channel system, as you can see it. And by the way, to the left, it is the channel system mapped using the conventional spectral decomposition application, which is the conventional stratigraphic interpretation. And you can see that we come up with almost the same shape of the channel itself. Even we come a very detailed information about, since the color as it goes to red, it means that could be the point bars at the kink area of the channel itself. So this and this and this. And then actually we posted the wells after doing this exercise, because this exercise is unsupervised, and they came up with conclusion that yes, you are dealing with 3 producing wells on this point bars, that including a lot of hydrocarbons in each of them. Then actually, not only structural and stratigraphy, but even if you are looking for a reservoir characterization and assisting reservoir properties, if you have inversion, then from that inversion, you can use this inversion and teach your computer, learn your computer how to follow up a separate or defined characterization. Say, I can say that I have a trend for 15% porosity. Then I can ask my computer and teach him that this is the shape, this is the neurons that will show you. In this case, it's going to be supervised, and this is a neuron that include 15% porosity, that has got some fluid, that has got some percentage of sand, some percentage of shale, and then I'll ask him to follow up this neuron, and then it will show and map it for me, and it will come for me with a picture in a 3D dimension that include all of the area, all of the similar area or hotspot area according to my volume. Yes? Then this will assist totally the same into reservoir properties and from the seismic inversion. Now, jumping to one of the most important part, which is the resolution. If your reservoir is a thinner reservoir and it is below the resolution, the seismic resolution, here is the solution where we are not restricted, as I mentioned at the beginning, we are not restricted into quarter lambda. No, we are restricted into the sampling interval, which could be 1 mils or 2 millisecond interval. So whatever 1 mils or 2 mils equivalent on the depth domain, this is your resolution. So if it is 5 meters, then your restriction with 5 meters. Of course, 5 meters is not going to be resolved on the normal seismic, but actually in here you can see it. And how that? I'm going to show you just a very simple example. To the left, this is a normal seismic section, and this is my zero crossing to zero crossing that include this nice red trough and this nice black peak together. Actually, this interval from the center of the peak to the center of the trough, now it is resolved into 1, 2, 3, 4, 5, 6 neurons. So actually 6 layers have been resolved, and I can see that even this dark red layer or brown layer is, you can see it here, and there's another layer, orange one, and a third layer could be green one in here. All of them I can follow up directly them. To the right one is my artificial intelligence resolution. To the left is my conventional resolution. Look how the difference is. Actually, this is enlarged to the right. As you can see, this is a correlation of that interval. So this interval on the correlation of the gamma ray and the other interval from the logs, you can see them into 1, 2, 3, 4, 5, 6, 7, 8. So 8 interval can be resolved in here on the logs. Those interval, you can see them on the resolution. If you went to the resolution of seismic, there is much there. In this case, actually, if you use this kind of resolution, you don't need sometimes even to upscale your logs when you are doing your velocity model, actually, or upscale your logs sometimes when you are doing another model, static model or so. Another interesting topics, fracture. How we can detect our fracture pattern in here. Actually, A, B, C, D, E, F are 6 displays in the front of you. A, this is coherency. Now, we use coherency attribute. B is the anti-track Schlumberger working. C, the maximum fault lake hold. D, the maximum fracture lake hold. Yes? And then E, deep learning based fault detection. And then the seismic gradient. Those are the 6 attributes have been used. And actually, now this is multi-scale and the fracture prediction with the CNN. Look at the CNN. If we integrated all of this attribute together, it will give you more or less the original trend. And even so, you can bring up which of those are dominant, which of those are open fracture, which of them are connected fracture by looking on the vertical direction as well. All of this can be done by using the artificial intelligence. Last slide, most important one, which is the DHI. Can we detect the DH direct hydrocarbon indicator directly from the seismic? The answer is yes. Yes, how do that? This is an example. Also, I think belonging to Geophysical Insights in 2017. This paper published in 2017. And actually, it is an interesting, this is a structure map. And this is a nice fault showing toward the south. And this is a nice anticline, rollover anticline on the south. And there is a nice well drilled on the downstream side of this anticline. And then this structure map have been covered by amplitude map. And you can see this nice red, yellow color and restricting more or less this area to the hydrocarbon. And then there is another area for the amplitude at that part. Then to here, actually, we run the attribute, different attribute of that volume, and then it come up with an interesting sum map. As you can see, the gray color in here is one color, while the green almost of all the area. So all this area have more or less green color, and what you can see here is one color, which is the gray one. Actually, the gray one is coming more or less restricted to the presence of the gas. So that directly, this is attribute or this kind of hexagon or neuron that got this color are restricted to the hydrocarbon. And even so, you can see it on that area. You can see it on that area, which is that area representing. And very interesting, there is something also happening there, and there is something happening there. So now, this is an interesting. Actually, they took a north-south line, as you can see it in here. There is north-south line, which is the line 9411, this one, perpendicular to the anticline. Yes, this line, north-south line, perpendicular to the anticline. And actually, what we are looking for, this is the south and this is the southern part, which is this part, and this is the northern part. And this is the area where our target is. You can see it. Then we restricted the neurons into three colors or four colors of neurons, which is the dark gray, and then the dark red, yes, and then this color that ranges from green to yellow. You can see that the dark red that looks like sometimes looks black in here, it almost horizontal. Then the same color is almost horizontal. Then the same color is almost horizontal. Actually, the well is there, and this is the oil water contact. So you got another closure. So you have not only one closure, two separate closure with two different oil water contacts. So this is what this section is saying. It's saying that there is a contact here and maybe another contact there. And then there is another contact there. And this is exactly what you can see. A third contact is there. And this is not drilled yet. Yes, so exactly, and what you see here as a dark gray is representing your hydrocarbons. So it is direct detection for hydrocarbon, very high resolution, detecting the oil water content. When you go to the third display here in here, you can see we just restricted the neurons into three neurons, which is the dark red, and then two gray, or color, pale gray and dark gray. The dark gray representing the hydrocarbon, the pale gray representing the background, just to separate and do the separation. Thank you very much. This is the last slide in my presentation, and looking forward to your question. And actually, the conclusion is using the artificial intelligence, you've got more or less 10x performance, almost 10 times you have the performance better. And then efficiency, you get 80% efficiency. And then also for you can make different scenarios at the same time, quantify the uncertainties that you have into your job. Again, thank you very much for listening, and I'm ready for any question.
Thank you so much, Dr. Ali, for this informative session. It was really beneficial. And thank you so much for your effort and time. We have three questions. The first question, why do we perform quantitative seismic interpretation in pre-stack rather than post-stack?
Again, say again. Why we do what?
Quantitative seismic interpretation in
why we do it?
pre-stack?
Yeah. Yes. Actually, quantitative interpretation directly we mean by the properties of the rocks itself. The engaged of the fluids, gases or water or formation water within the rock. You cannot do this kind of interpretation on the post stack. On post stack, everything has been, as you can, if you understand the principle of AVO, then in order to see the AVO, the amplitude versus offset, you see it on the far offset. So you need to have the near offset and you have the far offset in order to look at the difference between them. At the same time, to see the echo of the gas. If you stack them together, then everything is stacked together. You will never be able to see it. That's why we do all the pre-stack, all the studies on the attribute on the DHI on the pre-stack itself. Application of the artificial intelligence will use both of them. Would use the far offset, the near offset, and even sometimes the mid offset. Not everything together. So it's essential to use the pre-stack data rather than the stack data.
Okay. Why hydrocarbon are often found in deformed area?
Why hydrocarbon what?
Are often found in deformed area.
Maybe I can look for the question if it's written. So because actually I cannot hear you in a good way. Let me first of all put your list. First, let me get into
in the Q&A section.
Yes, I will go to more. Yes. Okay, the question, why hydrocarbon are often found in a deformed area fault? In seismic interpretation, we often listen about fault. That's good. That's a good question, actually. Once you have fault, this means there is some sort of rotation of the bed, and the rotation of the bed will bring for you depth, and the hydrocarbon migrate from the lowest depth to the highest depth. from the basin to the highest land, relatively. So that's why it is the fault sometimes work as a barrier from as a trap for this hydrocarbon from moving in another direction, or sometimes at a gateway. It will sometimes the hydrocarbon will go through the fault and go to the other side. So there is a trap that the fault is sealing, and in this case, it's trapped by the fault, or the fault is not sealing. Then the hydrocarbon will migrate from the both sides of the fault. In this case, the fault is not sealing. And actually, this is one of the parameters that we all the time we have to calculate it to see if the trap is working or not. Okay. Third question: how reliable is the result of automated seismic interpretation, and how do we QC the result? This is another good question. Reliability depends on the measurements. If you if you have your work done as we did on this exercise on conventional way, so you do all the tests using the conventional, and then you do it in the other side to just convince yourself that it is the other job. You do it using the AI. But actually, we are not. If you do this the same, this means that you are going to more or less cross the AI, because you by end of the way you are doing the job twice. But actually, as you can see structurally, you can look at the result of the AI visually. So you can animate your volume. You look at the work of the AI itself. Either it's like what the last example that I showed about the stratigraphy. You can look at your volume. You can extract your volume and you see this with this volume using the wells themselves. So there's a lot of QC steps that you can do it step by step, not at the end of the project itself. Okay? Any others?
Okay. Thank you. Thank you again so much. Thank you all for attending. Highlighting this session is recorded and will be uploaded soon on PioPetro YouTube channel. So make sure to subscribe in our YouTube channel. Thank you all and bye.